All right, y'all, it's Barry. We're going to get into our Unit 5 notes here, circular motion. We're going to look at how going from moving in a straight line, forwards, backwards, acceleration, the momentum of an object, the kinetic energy of an object, all that good stuff changes once we start moving something in a circle. And short answer here, it's the radius. That's all that's really the key. So we're going to get into all this stuff and talk about how it works. You're going to see some symbols that you haven't seen before. And really, it's just a conversion from moving in that straight line to moving in a circular path. So let's get into it. First thing, our big ideas. We're covering all 5 of the big ideas that we've hit so far. We got objects and systems happening here with a mass. We have fields that are going to exist. Gravity is still going to be a part of this to some degree. Interactions of objects with other objects are going to be described by these forces. We're going to result in changes in systems here because of those forces acting on them. And interactions are going to be constrained by conservation laws. So we're hitting really all of it. And again, we're going to be looking at all the units really that we've covered to this point, just changing the path through which these objects are moving. In order to do that, we need to look at really the difference here between lines and arcs. And so an arc is a part of a circle. It might be half of a circle. To be honest, it could be like 3 times around the circle, right? The arc really is just the path that an object takes in a circular direction. And so what we're looking at here is a line basically being bent around to form into an arc here. And if you look at what we've got down here at the bottom, if we take this object that maybe was a straight line, like you see right here under the words arc length, and bend it around into a circle, we just get this shape right here. And so we would describe this now by the radius of that circle, as we describe all circles. And then if we are having that motion from, let's say, A here over to B there, the change in the angle on the inside here is what we're going to use then to describe that S, that arc length. Okay? Now, the key here is we're going to need radians for this, and that's really, really important. In AP Physics 1, that's algebra-based. So far, we've been using degrees. We need to use radians for this, and we'll get a little bit of practice of that once we get into class here. But a quick reminder, 360 degrees is equal to 2 pi radians. Now, as we go through this, again, so we've got this object moving in a linear path here in a straight line. It's now going to be moving along this arc in this circular manner, and so we're going to have rotation of an object maybe around the outside here, or potentially of just a circular object moving around and sitting on that. So say you're on a merry-go-round or something like that, and you're moving around in that continuous circular pattern. You're going to have a tangential velocity, and that tangential velocity is what we've been used to as far as velocity goes. And you see the velocity moving right there. But once we start spinning, now we have an angular velocity, this W. And the key between the two, as you see down here in this small equation, and we're going to go much more in depth into this in just a couple minutes, but the key between them is that radius, okay? So really, we're just looking at the same type actions as far as physics is concerned. We're just moving in a different path here around a circular path. So the first thing we want to talk about is position. Right, in the past, we've talked about position represented by x. Right here, our position is x equals 3. Well, in rotation, we're going to talk about position measured from how far of a change in the angle we have. So here, this object that's right here, instead of being saying on this line, we would just say x equals 3. Here, we're going to say, okay, this object is located at this little yellow dot right here. Instead of describing where it is as far as just x equals whatever, now we're going to say it's at angle theta and radius r. Okay, so we're just going from x to theta and r. And that's really the only difference here, okay? So if we were to look at the displacement of it, now we have, right, 4 to 0 here. Our displacement is -4 for this first part, okay? And that's what we've looked at so far. In the case of our circular motion now, we would say, okay, there's a change in this angle as we go from yellow to the black dot here that's delta theta as opposed to the delta x. It's gonna be at the same radius throughout, so we don't have to state any change in the radius, okay? It's going to be at the same radius as it rotates. We just have this change in the angle at which it's located. So delta x becomes delta theta, and that's all there is to it. Now the arc length, right here, this s, how far it's actually traveling, is going to be based on these two objects as we looked at just a minute ago to start this off. So you're going to see there that length, that arc length, is in meters, is going to be the radius in meters times that delta theta that's going to be in radians, but that's not a unit that will actually leave on there. So it would be, let's say, r as 2 meters times delta theta, which could be pi, right? So just pi. So it would be 2 meters times pi equals the arc length, and that would give us that arc length in meters as well. All right? Okay, to look at speed and velocity as these things change here. So we've gone from a velocity that's in a vector direction, like you see here with this VT, this tangential velocity. But imagine that object is trying to travel with this velocity right here, but there is something, let's say the object is rotating around, it's a tennis ball on the end of a string, okay? And it's rotating around given the radius that it's being held at. Well, it wants to go this way, but because there's this string holding it, it continues on this arc. So it's going to have this tangential velocity. Like if you were to let go of that string, it's going to fly off in this direction if it's right here, or in this direction if it's right there, or in this direction if it's right there. That's what a tangent is. That's why this is the tangential velocity. But it's going to continue to rotate if the string is held, okay? So the same particle will rotate with an angular velocity now, w, okay? And this w, this angular velocity, is going to be equivalent to just v. So we see v ds dt up here, right? Where s is the arc length. It's like our dx dt, how far it's gone and how much time. Well, now it's going to be that change in angle, theta, divided by the change in time. And so all we're really doing is correlating these units to say, okay, what was tangential velocity, our straight line velocity, was the change in the meters divided by the change in the seconds. Well, now we're going to have our angular velocity, which is our change in the angle divided by the change in the seconds, the change in the time. And you're going to see this throughout here. The radius is the correlation between these quantities. So where velocity in a standard direction here is our measure of how quickly something's traveling, now that it's our angular component of that, our angular velocity, if we were to take that and just multiply by the radius, we would get the actual velocity that it would be traveling at if it were let go, okay? So the radius is going to be the correlating factor in all these different cases. That's going to be true here for our acceleration as well, okay? So we could spin this faster or slower. And normally if something's sped up or slowed down, it would be a change in the velocity over a change in the time. Well, if we were to have an angular acceleration, it were to spin faster or spin slower, that's going to be a change in the angular velocity divided by a change in time. And again, the correlation there is going to be that the standard acceleration will equal our angular quantity, our angular acceleration, times the radius. Now, there is something else known as centripetal acceleration. And centripetal acceleration is a measure of the actual change in direction as opposed to a change in velocity. And you see it right here defined as v squared over r. We're going to get into that a little more on the next slide, but it describes the changes in tangential velocity as an object rotates. All right, so this vt, the changes there. Now remember, velocity is not speed. Velocity requires a magnitude and a direction. And that's what we're going to get into right now, okay? So this centripetal acceleration, it describes a change in velocity without a change in its magnitude. That sounds weird, okay? So let's say you're traveling at 20 meters per second. And if you travel in a straight line at 20 meters per second, you have no acceleration. But if you travel in a circle at 20 meters per second, you do have an acceleration because velocity is both magnitude and direction, and your direction is changing. Now, you've experienced this. If you have gone around a curve in a car, you feel a pull to one side or the other, depending on which way you're turning in your car, right? You've all felt this before to some degree. That is the force that's generated from this centripetal acceleration. That's known as a centripetal force, okay? So velocity, remember, is both direction and magnitude. If an object moves with a constant tangential velocity but changes direction, it still accelerates. And we see the acceleration that we could measure down here, v squared over r. That accounts for that acceleration, that change in direction without there being a change in velocity. All right? And a reminder there, right? Net forces and Newton's laws, and all of this holds true here as well. And then you see the quantities plugged in here that will get you your your circular centripetal acceleration as well. And it's really just a substitution of that v for the r there that we looked at earlier. All right, so the key here for these basic components, once we start moving in a circular direction, is that we are just changing some of our quantities to look a little different because the path has changed. Now, our kinematic equations are still going to hold true, Okay, and these are going to be on your equation sheet. You can check these out. We see how this is changing from linear form here when we're moving in a straight line to our angular form when we're moving in a circle. So reminder, v, velocity, becomes angular velocity. Same thing for velocity there. Our acceleration becomes angular acceleration, and this still holds true just like this did. We're just changing the path in which they move. So you don't have to relearn all these concepts. We just have to change the orientation at which we're looking at this object that's moving. So our second kinematic equation here as well, same thing. X becomes theta. So this is a measure of the angle, of the amount of rotation, as opposed to the position. And all of those quantities change. And then V to W and A to alpha. So same things there. And it holds true for our third kinematic equation as well. So really, for circular motion, all we're doing is changing in our minds the way that we're looking at these quantities from going in a straight line to moving in a circular path. And we're going to get a bunch of practice with this, so don't worry. The next thing we need to look at is inertia. And so far, we've looked at inertia simply as mass, right? The mass of an object is how we are describing the law of inertia as far as Newton's laws. So this is from Newton's first law, known as the law of inertia. And it's defined as the natural tendency of an object to resist changes in its motion. All right, so a lot of mass, hard to move, small mass, easy to move. This is why F equals ma. And for translational motion, again, it's simply mass. The more mass, the more likely an object is to resist a change in motion. So we see this person here with some inertia as they are moving. Now, the key is if we were to watch this and this were a video, they almost certainly aren't going to stay still like that, right? They're going to begin to rotate. And now that we're looking at this circular and rotational motion, we need to consider how quickly or how slowly they're going to rotate as they go flying off this bike as well. And hopefully they're unhurt. All right, so rotational inertia. In a system that is rotating, there's two types of motion happening at once. So if an object is moving from here to here, it is moving, and we can look at it just like a point and like it's moving, like we've done so far. But if it's also rotating as it's moving, say you throw an axe from here to here, then there's that rotation that we need to take into account as well. So we must add inertia that includes the rotating action. And the key here is the distance from the center of rotation for the masses must be taken into account. So we have this hatchet right here. It's going to be more massive or denser in the metal part than it is in the wooden part. But if I look at just a piece of wood, this is probably its center right there. And so if it was just a piece of wood, it would rotate about this point. But because I have this heavier portion here, the center of mass, okay, the center of mass is not going to be right here. It's going to be probably more like right in here in this little piece that's tucked in, because then it's about equal mass all around it. And that's the point it will actually rotate around. Okay, I'm not encouraging anyone to go throw a hatchet in their backyard, but if somebody were to throw a hatchet, that's what we would see. We would see it rotating about essentially this point that's right here, because then it's approximately the same amount of mass all the way around it. Right? So inertia and rotational inertia, the way that we would find that, okay, again, it was equivalent to mass when we were looking at linear motion, but here it's going to be the rotational inertia, and it's going to be I, this is a capital I, rotational inertia. It's going to be the sum of the masses times the radii squared. Okay, so I'm going to go back real quick to this and look at this. So we would break this basically into two parts because it's really two things stuck together. I would say, okay, right here, the center of mass would be the radius that I'd be looking at, like right in here. That's the radius I would consider, and then the mass of the handle. And then I would look at this piece right here, and I would say, okay, the center of mass for this is right about here, and I would look at the radius from that as well. Okay, and we're going to consider then both the mass and the radii, how far out it is from those spots for both of these pieces. And this is why instead of it just being around the center of the handle, it's going to move up in this direction because the mass is up here, and then the radius will be somewhere in between those two radii, and we would have our rotational point up here. We're going to get into some examples of this as well. Okay, so our inertia for rotating objects is mr squared. And we would add, the reason it says sum of mr squared is we would find mr squared for the handle in the hatchet example, and then for the head as well, and we would put those together to determine our total rotational inertia. All right, now, if you have an object that's rotating here, this is going to go into something called angular momentum, and we're going to get to this coming up soon. But if you change then the length at which things are rotating, we're going to have a big effect then on W, okay? And the inertia is going to be really, really important when rotating objects are changing to some degree, because that radius is really what determines, as we just looked at, the radius is what's going to determine how quickly or how slowly you are rotating. And so changing, making smaller or larger that radius is going to have a drastic effect on how much rotation is actually happening here. So a quick sample problem. We have a 2 kilogram mass and a 3 kilogram mass. They're mounted on opposite ends of a 2 meter long rod, of negligible mass. So basically we have a 2 meter mass or 2 kilogram mass and a 3 kilogram mass, and they're 2 meters apart. All right. I want to know the rotational inertia about the center of the rod and about each mass. So if this was my rod, the first one I'm asking for is if it rotates about the center, like this. The next one is about each mass as they're on the ends. So this one would be rotating like this. And then the other one would be as if it rotated like this. Okay? So we're going to look at those 3 different examples and how that inertia changes for each. And it's going to, because the masses are different on each end. All right, so the first one right here. We're going to say for this first one that we're rotating about the center point. If it's 2 meters long, then this 2 kilogram mass is 1 meter away, and the 3 kilogram mass is 1 meter away. And I'm still going to use mr squared and add them together for each. Okay, so the 2 kilogram mass, again, we're right here. We're rotating about this center point, right? If this is a meter here for the 2 kilograms, I get 2 kilograms times 1 meter squared, and then 3 kilograms times 1 meter squared. And that's where I get this. Now, in the case of this one rotating about the 2 kilogram mass, there is no radius here for this mass, right? So all I'm looking at is the 3 kilogram mass that is now rotating at a 2 meter distance. And so I get 3 kilograms times 2 meters squared, 12 kilogram meters squared. And then if I go the other way, I have this 2 kilogram mass at 2 meters, and so it's rotating like that, and we get 2 kilograms times 2 meters squared. All right, so a lot of this is going to be frame of reference. We've talked a lot about frame of reference so far, and that's going to be a big part of what we're looking at here as well. So this right here is going to go ahead and show us some of these things that are going to be coming up here if we look at moment of inertia instead of mass and some of the other correlations that we need to make, because this stuff is going to hold true for forces and kinetic energy and momentum and our work energy theorem, and all that stuff is also going to shift just slightly for our new quantities here, okay? And so we'll look at how all these work, and I've got this at the end of this as well, so I want to make sure that you see the correlations there in the same way we looked at the kinematic equation correlations. Now, solid shapes. Solid shapes are going to have varying inertia as they rotate about different things. So this object right here, spinning, is going to have some inertia to it as it spins, okay? And this would be like right here, if I had the axis right down the center and it spun about the center, the inertia of it we could find here just with mr squared over 2. And this is going to be true for all solid-shaped rotating objects. Now, if I were to look at it like this and it rotates about the center axis here, okay? So first one was like this with the axis right down the center. This one is rotating like this with an axis right there, then I would look at this right here and say, okay, now this is my inertia, right? mr squared over 4 plus, what have we got there? Looks like ml squared there over 12. And so these are things that would be for specific solid shapes. Now, there's going to be a lot more than what's shown here. And if you are asked to find the inertia of a rotating object like this about a center axis, you'll be provided with the equation that you need to use. Okay, but I wanted to give them to you here to at least talk about them and have them mentioned before you might have to actually use it. So what we're going to do now is we're going to get into the other quantities that we've calculated up to this point and determine how they would change based on a rotational path as opposed to a straight line path. We're going to start with kinetic energy. Okay, so kinetic energy in the past has been 1/2 mv squared. Now m has become I, right? Because the mass is translating over to inertia. And v has become w because the tangential velocity is changing over to our angular velocity. So what we've got really are our translational kinetic energy, the same type of kinetic energy we've already looked at, and our rotational kinetic energy, which is going to be how it rotates there. So to go back to our hatchet example, If I were to throw that hatchet, it's moving from A to B, and we could find 1/2 mv squared, the translational kinetic energy of this as it's moving. We could also find then the rotational kinetic energy based on how quickly or slowly it spins. So I could throw it so that it spins very quickly as it goes from A to B, or so that it spins very slowly as it goes from A to B. It's still going to go from A to B, and if it goes with the same velocity in both cases, it'll have the same translational kinetic energy. But it's going to have a higher rotational kinetic energy if it spins faster than if it spins slower. The total kinetic energy for these things will be found here by adding those two together. So the total kinetic energy will be the translational kinetic energy plus the rotational kinetic energy. And I just said kinetic energy a lot. All right, so to take a look at an example of this. We have a solid ball, baseball, something like that. It's 300 grams, and it has a diameter of 8 centimeters, so a radius of 4 centimeters. It's thrown at 28 meters per second. As it travels through the air, it spins with an angular speed, so it's thrown from A to B at 28 meters per second. It's spinning at 110 radians per second. Okay, so it's doing both. So we have a pitch in baseball that is a curveball or something that has rotation to it, not just like a knuckleball that wouldn't be spinning at all. All right. We want to find the translational kinetic energy, the rotational kinetic energy, and then the total, which will just be those two quantities added together. So rather than try to have y'all pause and go through this, I think seeing some of these examples to start us off here is really helpful. So same problem up here at the top. The translational, 1/2 mv squared. Boom, there we go. Okay? I mean, just what we've done before. You've had a lot of practice with this. There you go right there. We've got our 1/2 mv squared. Now to look at our rotational, first we need to know how to find the inertia of that object. And so if I went back up here and looked at a rotational object here, right? I've got 2/5 mr squared for a solid sphere about any diameter, 2/5 mr squared. And so that's what's going to be used right here to find our inertia. All right? And so you just use that for that I because it's rotating about that center point. That's what we're going to use. And then it's rotating at 110 radians per second. Radians per second. Right there, we're squaring this value, and we end up with this very, 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 very small rotational kinetic energy. And what this tells us is, okay, this object moving from A to B generates a lot more energy than the spinning it has as it does that. So really, we're going to have 118 is going to be our total here in this case because it's a very uniform shape and because the velocity at which it's traveling at, 28 meters per second, is going to be much more significant than the spin, 110 radians per second. We're going to have mainly in the end here translational kinetic energy, but we can find both. And in this case, this one just happens to be negligible. All right. So if we have kinetic energy, as we just covered in this momentum and impulse and collisions unit recently, then we've got to have momentum also, right? Kinetic energy and momentum in a lot of cases go really, really well together. So angular momentum, this is going to be a quantity that tells us how hard it is to change the rotational motion of a particular spinning body. It's going to be very similar to our momentum, mass times velocity. We're just going to have those small changes that we've already talked about, all right? So objects with lots of angular momentum are hard to stop spinning or to turn, and objects with lots of angular momentum have great orientational stability. A great example of this is a top, right? You take a top and you pull the cord on it or something like that, and you spin it, and it gets going really quickly. And the quicker it spins, the more straight up it stands. But as it slows down in its rotation, it wobbles, right? Starts to wobble, until it's not spinning very quickly. That's when it falls down. So angular momentum causes rotating objects to have great stability, and that's why this is really important. Now, the angular momentum of a particle, of a single particle with a known momentum, P. Momentum is P, that would be mass times velocity already. The angular momentum will just be that times the distance from the particle to the point of rotation. So an object such as this, that would be rotating like this. Well, I could find the point on the outside here and find its mass and velocity as it's going around, right? So mass times tangential velocity, that would give me my momentum. The radius from the center there is then going to determine what my linear momentum, my angular momentum is going to be in that case, okay? So for a solid object, angular momentum is analogous to the linear momentum for the solid one, right? So P is mv, the linear momentum. We're going to replace our quantities here with angular. And that's really the end goal with all of this, right? So we see that, I don't like that that's capital, apologies. There we go, that looks more like it should. Our momentum is normally mass times velocity. Well, again, mass is now becoming I, inertia, and V, velocity, is becoming W, angular velocity. And that's all we're really changing. Okay, so in the end, we're just changing the mass to inertia and the velocity to angular velocity, or the, again, position to displacement there, right, to our angular displacement, and our acceleration into alpha. All we're doing is using the same principles we used before, but changing to these circular quantities. So, law of conservation of angular momentum, this is important. So this states that the momentum of a system will not change unless an external force is applied. Friction can be an external force, so keep that in mind, but if you see ignore friction, then we're going to have a constant angular momentum throughout. All right? So how would you change the statement to create a law of conservation of angular momentum? We're just going to say it's not going to change unless an external torque is applied. And we're going to get to torque, but torque is basically force applied at some radius in that circular direction. We'll get to that in just a minute. So again, conservation applies. We're going to have the same momentums here continuously. All right? So a quick example of this. So a figure skater is spinning at an angular velocity W. So W naught, right? Our initial angular velocity. He brings his arms and legs closer to his body and reduces his rotational inertia to half its value. So to go back and look at this, right? So we have this W. If I goes to half, we're going to have the conservation of angular momentum. So L is going to stay the same. If I is half, what's going to happen to W? What's going to happen to the angular velocity? It's going to double, essentially. 1.5, the other doubles. And this is why we saw this image earlier where, okay, we've got this full radius here. Well, if this gentleman pulls his arms in so that the radius is half, he's going to be spinning twice as quickly. That's what we're looking at, okay? Because that angular momentum is conserved. All right, so this is where we were right there, okay? So to move on, last little bit here, we're going to look at statics and equilibrium and what it means to apply a force at some radius in a circular manner. So, well, here, let's just kind of build on this from right here. So statics, this is the branch of mechanics concerned with the analysis of loads. So force and torque, or the moment about a location on physical systems in static equilibrium. And this is imperative to the study of keeping things like buildings standing, right? If you've got a very, very large building, wind is going to push against the side of it. And it's going to try, if your building looks like this, to push on one side and knock it over. And what you need to do is make sure not just that it's strong enough to stand up, but that there are the correct foundations in it to keep a force applied at some height where the wind is maybe the strongest from knocking it over and from it rotating about this point. And that's why I say here this is civil engineering. And I hit that very specifically because I have a civil engineering degree. And this is something I've spent a lot of time doing. So this is one of the pieces of this class that I really like, is specifically the statics here, the equilibrium situations for this unit. So to look at static equilibrium, a key in this case is going to be that the sum of the forces are 0. All right. That is our equilibrium of forces. That's our net force being 0, right? That's our situation where we have no acceleration. And so up here, when we see just our forces, there'd be no movement, right? Now, what we're going to switch to is looking at this right here, where we have essentially a balancing act going on, all right? Now, you see here, the normal force, and well, this object here, N1, is larger than N2. But they're going to balance about this central point if the distance for 1 is proportionately less than the distance for 2. And so what we end up here is with a force applied, in this case gravity, right? If you're on either side of a seesaw, then it's the force of gravity that's being applied in those situations, times the radius to that center point. And so we're still looking about how these things are making some motion here about this bracket in the center. So it would go one way or the other based on where they're at. And so if we were to scoot this in and leave this one here, then this is going to actually go down, because the quantity of the force, or the weight, times the distance will be less than what it is here when it's in equilibrium. So really, again, we're just looking at that distance to the center point, or the radius. That's what we're looking at here, okay? So torque is when an object rotates because of an applied force. So we've got right here, we're tightening a bolt, right? So a force is applied to this wrench, and it's causing this circular torque to make this tighten. So in order to determine the amount of torque, we need to know the force applied and the distance from that center that it's applied. So when we calculate torque, we're looking at the radius times the force. And so whenever we saw in some of these equations earlier, what would have been a force previously, now we're going to see a torque for angular objects, right? And right here, right, where we had a force, now we're going to have a torque. Okay, so it's going to be all the same ideals and physics concepts. We're just changing out these quantities so that it's moving in a circular manner. All right, so to calculate torque, we looked at this already, apologies. So a quick example here. A plumber is using a large wrench to shut the water line off to a house. He places his left hand 1 meter down the wrench and pulls with a force of 20 newtons, and his right hand 2 meters down the wrench and pulls with a force of 10 newtons. Which hand generates a greater torque? And what is the total torque generated? Now, again, we know right here, this is what we're looking at, 1 meter, 20 newtons, 2 meters, 10 newtons. Now, one thing that's very odd here is this person apparently has 2 right hands. But I don't know what to say there. I didn't make this image, so it is what it is. All right, but we've got 20 newtons times 1 meter, 20 newton meters of torque here. 10 newtons times 2 meters, 20 newton meters of torque there. And this is why wrenches in a lot of cases are made larger or smaller. The larger the wrench, the harder typically it is to use it, or the harder that it's designed to use on, because it's going to require more torque. So you can pull with the same force, but the further down you get, the more torque you'll apply. So applying that extra torque is what makes the job easier to do in this case, okay? So we're back to our big ideas real quick, and we're not going to wrap up totally yet. I'm going to go back to one more thing here at the end. But remember, we've got all 5 big ideas. We're using all the same ideas and concepts that we've looked at so far. We're just having objects move about a central point, so there's going to be some radius applied to this as they do so. Now, I wanted to give you this, and we'll do an activity in class also, but this quickly shows the correlation from one quantity to another as far as linear versus rotational motion. So again, position X becomes theta, V, W, A, alpha, so forth and so on. This holds true for all of our kinematic equations. Mass becomes inertia, and so it holds true for all other quantities where we have gathered how motion and how objects are moving previously as well. Right? And then the last little bit here, to show you this one more time, and more than anything else, I want to show you that these are at the end of the notes for your reference later on if you feel like you need them. But Newton's second law with forces, force is ma, now becomes the torque equals the inertia times the acceleration, the angular acceleration. We've got our momentum change here too, m to I, v to w. Our kinetic energy change, m to I, v to w. And so our work energy theorem is going to be the same as well, right? So work going into something is going to cause a change in kinetic energy. Well, now we have a torque going into something, moving something so far is going to cause a change in a rotational kinetic energy. Again, I realize that a lot of this is new language, but it's the same concepts. They're just being applied in a circular path. I hope this was helpful. We'll get more into all this stuff in class.